All right. Hello, everyone. Let's see. Hopefully, I have my mic actually muted over here. Good. All right. Sorry, I had to. My computer here decided it was going to do an update overnight automatically, and I had a bunch of stuff prepped, and then it was gone. But we should be good to go now. Let's get this countdown out of here. All right. So, yeah. So today, or starting today, we're going to sort of move away from multivariable calculus for a bit. Though we'll make a brief return to it, and we'll talk about how what we're working on here applies to multivariable calculus. But we're going to make a return to single variable calculus and kind of study this for a little bit, because this stuff is actually really important and really interesting. Because all this stuff about series and what we're going to call power series, most of the time when you can't integrate a function, this is a technique we can use. All right. So, and it's a great approximation tool as well. And depending on how time for things goes, we may or may not spend some time talking about, approximating functions with this stuff. All right. Anyway, let's go ahead and get started here. So really, this problem set has two problems, but each problem has like some subproblems. So there's like 7 total here. Let's go ahead and get started. Problem 1. Oh, sorry. I need to bring the Google Meet window back. There we go. All right. So problem 1 here, we want to look at this sequence here. Start with something simple. 1, 3, 9, 27, 81, and so on. All right. So we want to do 3 things here. We want to find the next 2 terms of this sequence. We want to find a recurrence relation for it. And we want to find an explicit formula for it. All right, so these are the same 3 things we did in the lecture videos for this. All right. So, when we're doing these problems, the first thing to do here is try and find a pattern that's going on between these. So here we went from 1 to 3 to 9 to 27 to 81. Right? And what are we doing from each term to the next one? Right? So we think about what's happening from here to here, here to here, here to here, here to here. We can see each time here what we're doing is we're multiplying by 3. So since that seems to be the pattern here, to get the next terms, I want to multiply by 3, and then whatever I get there, I want to multiply that by 3. Okay. So 81 times 3 is 243, I think. I hope. And then that times 3, it's something that ends in a 9, 729. That seems believable. I think that's right. All right, so those are the next 2 terms in the sequence, right? This would be A6 and A7 if we were to call the terms of the sequence, A1, A2, A3. Right. Everything looked good so far. Any questions? All right. So, all right, so that's that part. The next part here, we want to find a recurrence relation, right? So the work we actually do in part 1 here really helps to set us up for finding a recurrence relation, right? In most cases. Sometimes it's a bit trickier. Let's go ahead here and look at this. So each time to move from one term to the next, we just multiply the earlier term by 3. So, here A2 is 3 times A1. A3 is 3 times A2, and so on, right? So, since I'm just multiplying by 3 each time, really what I'm going to say here is that an plus 1 is 3 times an, because each term is always 3 times the previous term. Right? And then remember, if I'm going to do a recurrence relation, I have to tell it where to start. I have to give it sort of a seed to build off of. Right? And in this case, that seed is always just the first term in the sequence. All right, sorry about that. So, what do we got here? So A1 is the first term in this sequence, and that's going to be no reason, really. You could do that as well. That would also be perfectly acceptable. So here, this stuff is valid for n equals 1, 2, 3. If you wanted to do, and so on. So this would be one way to do it. Actually, normally we would write these in the other order. Another thing, you're exactly right. You could say an is 3 an minus 1. Actually, let me write this in the better order here. Let's write a1 is 1. Then if we wanted to say an is 3 an minus 1, which again, perfectly acceptable to do that. Then we would say here n starts at 2, 3, 4, so on. Right, so really what we're kind of doing is adjusting what n value we start at here. What n value we can start using the recurrence relation at. That's really the main difference. So it's what's called like a re-indexing of the formula. But yeah, that's a great question though. So whichever one you prefer, really. Yeah, whichever one you prefer is the one to go for. All right. Any other questions? Great. Yeah, so let me box this one as well, because this is another perfectly acceptable one. I'll say either one you want. All right. And the order you write these two things in doesn't really matter. Okay. Part 3 is we want an explicit formula. So for the explicit formula, this is where I think that chart is really good. At least this always helps me organize my thoughts on this stuff. So here we're going to make a chart, and we're going to write n equals 1, n equals 2, n equals 3, n equals 4, and we'll add more columns if we need to. I like making these columns a bit wide so we have some room to try and write out a formula in. Right? So here, we're starting at 1, then 3, 9, 27. Right? Actually, let's go ahead and write a 5th one, just so we can be sure. All right, and then the next one's 81. All right, so let's look at what we got. So to go from here to here, I've multiplied by 3. So I'm going to write down here, this is 1 times 3. Right? Because I took the old one and I multiplied it by 3. To get from here to here, I multiply by 3 again. So that's 1 times 3 times 3. So 1 times 3 squared. Here. So actually, for the first term, let me just write a 1. Right? Going from 3 to 4, I take 3 and I multiply it by another copy of 3. So 1 times 3 cubed. And this one is 1 times 3 to the 4th. Right? Because each time I just keep multiplying an extra 3 on it. Right? And if we look at it like this, where we don't actually multiply the numbers out, we just keep applying the pattern over and over, but never really sort of simplifying, so to speak. Sometimes you want to simplify, and you'll see that as time goes on. You'll see some that are better to simplify, some that are better to not. Right? So here, we can look at this and try and build up a pattern. Right? So here we see, the power on 3 keeps increasing by 1. It makes sense to say this is 3 to the 1 here. Over here, this would be a 3 to the 0. We can fill that in to kind of make the pattern look nice. And then this gives us a hint at what we need to write for our explicit formula. So an, we could write 1 times 3, and let's see. The power on 3 is always 1 less than the index, so it's n minus 1. And of course, this 1 here is a bit unnecessary, so we could just write 3 to the n minus 1. But I kept that 1 there the whole time because, if we start at something like 4 or 2 instead of 1 here, that number would be out front still. Right? So this formula applies for n equals 1, 2, 3, onward. Right. So, any questions about that one at all? All right. Okay. Let's look at problem 2 then, or part 2. Right. So here we're looking at the sequence that's 5, negative 5, 5, negative 5, 5, and so on. Right. So looking at something like this, we want to answer these same 3 questions. What are the next 2 terms? What's a recurrence relation? And what's an explicit formula? Right. So this one is probably a little straightforward, or a little simple, hopefully, to figure out. Right? So here, the next 2 terms, right, if we observe what's going on here, we have 5 minus 5, 5 minus 5, 5. Each time here, we're just changing sign. So if you like here, you can say this is times negative 1, times negative 1, times negative 1, times negative 1. So, what do you think is going to happen next? We're still going to keep multiplying by negative 1. And so the next 2 terms would be minus 5 and 5. Right? That one's probably not much of a surprise. Right? Okay. So, that's great. Oops. Now let's look at trying to find a recurrence relation here. So this one kind of works out the exact same way as the problem, or part one of this problem did. Right? Each time here, we're just multiplying by a number. So what we have in this case is that, an plus 1 is negative an, right? Because we just keep switching sign back and forth, right? N is 1, 2, 3, and a1 is 5. Right? Maybe I can put some semicolons between these. And again, if you wanted, you could also say, well, an is negative an minus 1. But again, here, n has to start at 2. And we still have to say a1 is 5. So again, either way you want to write this down is completely acceptable. Both of them are completely fine. All right. So, any questions there? Great. So let's look at the third one here. The third part, explicit formula for this, right? So this one probably doesn't require the whole chart to work out. Because here we can see that we're just going to keep multiplying by negative 1 and flopping back and forth. So a little tip here for this, when you have something that's going to alternate sign back and forth, you're going to use this or this one. Well, this one or this one. Either one is fine. These both sort of do the same thing. Whether it's plus 1 or minus 1. Usually you just pick the one that kind of works better for you. So here, this one, the negatives, this is negative in odd indices. So when n equals 1, 3, 5, 7, so on, that's when this one's odd. Either of these are negative in even indices. Right, so when n is 2, 4, 6, 8, 0, that's when these are negative. So if you have something that's going to bounce back and forth between positive and negative numbers, there's a decent chance you're looking for one of these. Okay? And here, we can say, all right, well, an, we know it bounces back and forth between 5 and negative 5. So we just need to take one of these here and multiply it by 5. And so our question is, should it be negative in the odd indices or the even indices? Right? And the way we've set it up, our first term is a1. Right? That's what we've kind of set up here. So it should be negative in the even indices, which means we should use one of these. So we can write it like this, or if you wanted, you could write it like this. Either one is going to be perfectly fine here. And this is valid for n equals 1, 2, 3, and so on. Right. Any questions at all about this one? All right. Let's go on to the third one. Now this one is really, really interesting and also really important, and I hope I wrote the numbers right. So here we have 1, 2, 6, 24, 120, so on. Right? So let's start with finding the next two terms. So here we have 1, 2, 6, 24, 120. Let's look at how we can, or actually, before I do that, let me suggest looking at this and see if you can figure out the pattern that's going on here. See what you could get. So there's a few things you could try, but only one thing's really going to work out here. Going from here to here, we're multiplying by 2. Okay. Going from here to here, we multiply by 3. From here to here, multiply by 4. Here to here, multiply by 5. So then the question is, well, what are the next two steps? Multiply by 6 if we're continuing this pattern, and by 7 if we're continuing the pattern. So multiplying this by 6 is 720. Yes, that's right. And then I can't multiply that by 7 in my head. So 720 times 7. All right, so the next term gets quite a bit larger, 5,040. But how does that look? Does that look like what you have, hopefully? Right. So hopefully this makes sense so far. Now let's look at finding a recurrence relation for this one. Because we're not just multiplying by the same number over and over anymore. We're multiplying by something sort of fundamentally different, right? So how do we set this up? When we're doing this, it can often help to just sort of write down, like, how do I get A2 from A1? How do I get A3 from A2? And so on. Right? So here, let's start out with this. A1 is 1, right? We have our seed value. A2, I get this by taking A1 and multiplying it by 2, right? A3, I get this by taking A2 and multiplying it by 3, right? A4, I get this by taking A3 and multiplying it by 4. Is that hopefully making some kind of sense for how this pattern is evolving? A5, 5 times A4, so on. Right. So use this and try and make a guess as to what an plus 1 is. Or if you so prefer, you can try and figure out, using an. So here, this would be n equals 1, 2, 3, so on. So either way, a1 is always 1. This one would be starting with n equals 2, 4. Right? So try and see if you can get your hands, or get a handle on this formula here. Any suggestions for this one? For either formula? I swear the tornado warning siren test. I know it's coming every week, and it always catches me off guard. All right. So here, if we look at the pattern here, we're always taking the previous term, and the number we multiply it by is this index here, right? So like, the thing we're multiplying a1 by is 2. The 2 matches here. The 3 matches here. The 4 matches here. So this would be n plus 1 here. Or if we used this version, this is n times an minus 1. And again, either one of these are perfectly acceptable recurrence relations. It's just a matter of, which one do you like better, which one suits the problem better. Usually that's how you're deciding which one you want to use, is, well, which one kind of works better for us. All right. Any questions on that? Okay. So, now for the more interesting part, which is finding the explicit formula for this one. So I'll make the chart again. N equals an equals. Right, so I always like starting my sequences with n equals 1. I mean, it depends on sort of what we're doing, whether you'll want to start at 1 or 0, the typical values. But really, it's kind of up to you. I personally like using 1 when I can. Right, so here we have 1, 2, 6, 24, 120. Right? And again, let's try and write out the pattern that's going on. So here, I have, this is just 1, right? That's all we start with. Here, to get from here to here, I multiplied by 2. To get from here to here, I multiplied by 3. Right? Going from here to here, we multiplied by 4. And here to here, we multiply that by 5. Right? So for each step of the sequence, what we're doing is we're essentially multiplying together all of the numbers starting from 1 up to whatever that index is. So an, then, the general term, we should expect that to be 1 times 2 times 3 up to, n minus 1 times n. Right? Multiply all the numbers up to n. Right? Does anyone happen to recognize that kind of expression? Does anyone know what this is called? When you multiply all of the numbers starting at 1 up to a certain point? Does that look familiar by any chance? So this type of expression is something we call a factorial. Right? It's red here. This right here is what we call a factorial. And the way we write this, and we're going to use this factorial thing a lot, is n with an exclamation point. Right? N exclamation point stands for multiply all the numbers starting at 1 all the way up to n. Right? Now the neat thing about this is, we know that exponential functions grow pretty quickly. Turns out factorials grow even faster than exponential functions. So, any questions about this one at all? All right, excellent. All right, so that's it for problem 1, unless there's any questions. Go ahead and move on to problem 2. And in problem 2 here, we just want to look at, what is the limit of some sequences. So we're going to write a few terms of the sequence, and then we're going to try and find the limit of this. So here we have the sequence an is 10 to the n minus 1, and n 1, 2, 3, so on. Okay. So let's write out the first 4 terms. So a1, if we plug in n equals 1, we get 10 minus 9, or sorry, 10 minus 1, which is 9. Right? Maybe we'll do this on the next line. A2, this is 10 squared minus 1, which is 99. A3 is 10 cubed minus 1, which is 999. A4 is 10 to the 4th minus 1, which is 9,999. Right, those are the first 4 terms. And all we do is just, pick the first n value, plug it in, and go from there. All right. Well, what does it look like this sequence might be converging to then? Or, the limit of this sequence would be? So this thing just keeps getting larger and larger, right? The magnitude of this just keeps getting larger and larger. So observing this pattern here, we can pretty confidently say that this limit is going to be infinity. right? In other words, the sequence diverges. Right? Any questions about that? All right. Let's go ahead and look at the part 2. Right. So the next sequence here is an is 1 over 10 to the n. Okay. And here, n is going to go from 1, 2, 3 onward. Right. So let's again write out the first 4 terms. Right. So a1 is 1 over 10 to the first, which is 1 over 10. Right. A2 is 1 over 10 squared, which is 1 over 100. A3 is 1 over 10 to the third, which is 1 over 1,000. And A4 is 1 over 10 to the fourth, which is 1 over 10,000. Right. So perhaps you can see already what's going on here. Sometimes it helps to look at this stuff in decimal. 0.1, 0.01, this is 0.001, and this is 3 zeros and a 1. Right? So following this trend, what do you think is going to happen to the limit? Writing A. So hopefully you can see here that this sequence is limiting towards 0. So we would say the sequence converges to 0. That's usually how we phrase that. So we can, look at this with these numerical tools, of course. Normally, the first 4 terms aren't typically predictive of a sequence. Usually we have to look at quite a few more. But in this case, the pattern is clear. Normally what we do here is we can, look at the explicit formula, and we can say, look, the top is going to stay 1, the bottom is growing, it's getting larger and larger. So just using our knowledge from limits from sort of first semester calculus, we can say, well, this has got to be going to 0. Right? So we can really treat these just like we treated limits, last semester. Right? Let's look at the third problem here. Right? The third one is an equals 4n cubed over n cubed plus 1. Right? Here n starts at 1. All right? So, let's go ahead and do our usual thing here. A1 is going to be, let's see, this is 4 over 1 plus 1, which is 2. A2 is going to be, let's see, 2, 4, 8, it's 32 up top and 9 on the bottom. Let's see, 32 over 9 is a number. All right, so this is approximately 3.5556, let's say. All right. A3, right, so let's plug this in. This is 4 times 27 on top. That's 108. Over 28 on the bottom, right? Because that's going to be 3 cubed, which is 27, plus 1. So let's see, 108 divided by 28. This is approximately 3.8571. Right? And A4, the exact value, so this is 4 to the 4th, basically. It's 256 on top, over 4 cubed, over 65. 256 over 65. This is about 3.9385. Right? So here's one of those situations where, you might be able to see sort of what this is going to start approaching, but you really can't base an estimate off of the first 4 terms. If you're doing it numerically like this, you have to start picking really large values of n. Say do n equals 10, 100, 1,000, and so on, and see kind of where that's going. Or we can use kind of our analytical tools, and we can say, all right, well, the limit as n goes to infinity of an, right? This is limit as n goes to infinity of 4 over n cubed, or n cubed plus 1. Right? And we just treat this like a normal limit, like we would have done, last semester. Right? And you have a couple options now. You can use L'Hopital's rule on this if you so choose. That'll get you to the answer. The other thing you can say is, look, the top is degree 3, the bottom is degree 3. So, since we're going to infinity, the limit is just going to be the ratio of the coefficients, right, of n cubed. So 4 on top, 1 on bottom. So this limit is 4. Does that make sense? Hopefully. Right. So here we would say the sequence converges to 4. Right. Another way to write this sentence here, if you want, is a common way to do this is say an goes to 4 as n goes to infinity. Right? These two say the same thing. Right? That arrow has always just meant, this goes to this. All right. So let's go ahead and look at the last one here. So here we have an plus 1 equals an over 10 plus 3. And here I'm actually specifying that a0 is 10. So actually our sequence here is starting at 0. That's fine. So we still want to write down the first 4 terms. The first term is a0, which is 10. Right? The second term, a1, right? Notice this is going to be a0 over 10 plus 3. So that's going to be 10 over 10 plus 3, which is 4. Right? A2 is going to be a1 over 10 plus 3. And that's going to be 4 over 10 plus 3. Which is, we can call that 34 over 10 if you want, or 3.4. Either way is really fine. Right? let's look at A3. This is the fourth term now, right? Because we started at 0. So this is, A2 over 10 plus 3. So this is 3.4 over 10 plus 3, which, depending on how you want to do this, if you want to write this as a nice fraction, this is going to be 334 over 100, which is 3.34. So what does this appear to be converging to is the question. That's a little hard to figure out, right? Little hard to get this explicitly just by looking at this pattern, right? We could try a bit more. You can figure out that A4 is going to be 3.334, right? And maybe you can see eventually what's going to happen here is, this pattern's going to continue. We're just going to keep getting more 3s like this. So it kind of, we're going to make a conjecture here that the limit as n goes to infinity of an is, 3.33 repeating forever, which is, that's a good way to write this. So this is 3 1/3, so 4/3 would appear to be where this is going. So, what I suggest, since we're kind of at the last minute here, what I suggest for this is try to plot this in Mathematica. So you have the document, the Mathematica document for this section. See if you can plot this and see if you can tease out this limit from there, right? So finding limits from a recurrence relation is always a little bit tricky. Often you want to try and turn it into an explicit formula, right? But anyway, that's it for today. Well, for this session, I should say. Let me know if you have any questions. Otherwise, have a good afternoon, and I'll see you on Friday. All right, hello. Let's start it here. Okay. Oh, let's get rid of the countdown too. That doesn't need to be there. All right. So basically got two problems here, but they both have multiple parts. So let's go ahead and get started here. I also have that camera thing I meant to turn on. All right. So problem one here. All right. Problem one, part one. Here we have the sequence 1, 3, 9, 27, 81, and so on. All right, so here's the first 5 terms of a sequence. And what I want to do for each of these problems in part one is, write down what are the next 2 terms, write down a recurrence relation, and write down an explicit formula. So let's go ahead and get started. So really, if you can do part one, it kind of sets you up really well to do part two. So if you can find the next 2 terms, it's going to make finding the recurrence relation a lot easier. Right, so let's go ahead and write this out. What I often like to do here is just write out my terms in a list and just say what I have to do to get from one to the next. Right? So going from here to here, well, what I'm doing is multiplying by 3. What I'm doing from here to here is I'm multiplying by 3 again. This is also multiplying by 3. It's also multiplying by 3. So then it shouldn't be any big surprise then if I want to go to the next term that I should probably multiply that by 3. And then if I want the term after that, I should multiply again by 3. Right? Hopefully that seems reasonable. Right? So, all right, 81 times 3 is 243. So that should be a good 6th term. Right? And then the one after that, if I multiply that by 3, 729. That seems like a reasonable choice. Right? Hopefully that makes sense there. So again, what we're really looking at here is trying to recognize the pattern to move from one number to the next one. And if we can recognize that pattern, then it becomes really easy to sort of generate the next term and the next term. Right? Okay. So that's this one here. Any questions there? Awesome. So, oops. So let's go ahead and go to the next part here, which is we want to write down a recurrence relation. Right? So this one's not too bad to figure out because we can sort of see, we know what we're doing each time to get from one term to the next. One thing that can help you sort of figure out how to write this down is, let's see, with a recurrence relation, we always need a seed value. So, A1 equals 1. You can start your sequence at A0. It's completely up to you, really. Normally you pick something convenient for the situation. If there's no sort of reason to start at 0 or 1, personally I start at 1, but you can really start this at whatever index you want. Right? So A1 is 1. Sorry. Then A2, I get that. So this is A2. I get that by taking A1 and I multiply by 3. Right? To get A3, I take the previous term A2 and I multiply that by 3. Right? To get A4, I take the previous term and multiply that by 3. And if you kind of write out a few of these, you might see like, oh, okay, I see what's going to happen here. The trend is, right, we have our seed value, and then an plus 1 is always 3 times an. That's what's always happening here, so that's our recurrence relation. And then we need to specify for this recurrence relation, what n value can I start with? And here it's 1. Right. So this would be a good answer. Right. One thing I do want to point out, because someone mentioned this in the last section, and this is perfectly okay. So I'll say another way to do this is we can still say a1 is 1, and then instead of using an plus 1 here, if we just say an, which is pretty reasonable to want to do, this would be 3a and minus 1, right? Because we're always getting an by doing 3 times the previous term. So either way you want to write it down, either recurrence relation is perfectly fine, as long as you have this relation. This could be n plus 4 and n plus 3 over here if you wanted. The only thing that really changes then is where n has to start here. So this recurrence relation will never give you the first term, so the smallest n I can put in here has to be 2. So in this one, n starts at 2. That's the only difference. So either of these, I would say it's preference, really, which one you want to write down, how you want to write your recurrence relations. So I'll leave that, up to you, whichever one you like better. But yeah, that's all there really is to the recurrence relation. Any question about that? Excellent. So let's go on to the explicit formula. Right, so this is the one that's sometimes harder to get your hands on, but is way more useful in doing computations. So the way I like to do these is to make this chart. Right, so here, n equals 1, 2. I like to make pretty wide columns for this so I can have some room to work down here. We'll do 5 of them. That should be enough. All right, and then what I'm going to do is I'm just going to write down the terms of my sequence. Right? And then what I want to do is try and break down the pattern as simply as I can. Right? So I just want to write out kind of how I move from one term to the next. And I want to write it out without simplifying anything. Right, so here we just have 1, this first term. To get from 1 to 3, we multiplied by 3. So I took that previous term 1, and I multiplied it by a 3. Right? Okay. Here, to get from 3 to 9, I took this, and I also multiplied it by 3. So that's 1 times 3 times another 3, but there's no point in writing 3 times 3, so I'm just going to call this 3 squared. Okay. Right? To get from 3 to 4, I multiplied by another copy of 3. So this would be 3 squared times another 3, so that's 3 cubed. Okay. And then, again, we multiplied by another 3, so that would be times 3 to the 4th. So when we sort of just break it down like this and have this kind of general pattern here, or just write down what we're doing at each step, but without like fully computing it out and writing 3, 9, 27, 81 again. When we look at it this way, it's a lot easier to see what the explicit formula is doing. Because what we're trying to do is see is there some, does it look like there's some function here that I'm plugging in, you know, n equals 1 for this, n equals 2 here, 3 here, 4 here, and 5 here. Right. So if I try to follow this pattern backwards now, this is a 4, 3, a 2, then this one, I should probably write a 1 here. Then it would make sense that, you know, adding on 3 to the 0 here. So if I fill that in, we know 3 to the 0 is 1, so this didn't change anything. But also, it makes the pattern flow nicely. And at this point, we can tell, you know, we want to see if we can associate the index to this pattern here. And if we look, the power on the 3 is always 1 less than the value of n. So in that case, we can figure out that an is 1 times 3 to the n minus 1. Or in this case, you can leave off that 1 because the 1 doesn't do very much. This is just 3 to the n minus 1. Right? And here, n starts at 1. And there you go. Right, so you know, you could leave it like this if you wanted. You can simplify it to this. The reason I left the 1 at first is like, you know, maybe we started here with a 4 or something, and then we just kept multiplying 4 by 3 over and over. In that case, you'd want to leave, you know, that number there. Right? Just as a little aside, if you did decide you wanted to start at n equals 0, perhaps, then your an would look a little different. It would just be 3 to the n. And again, that's if you start at n equals 0. Right, so different starting points can change how your explicit formula looks. But, you know, that's up to you. So here, you know, this one would be A0, this would be A1, this would be A2. It really depends on what you want your starting point to be. Right? All right, so maybe I should add in here to clarify, this is if we start at n equals 0. So this chart doesn't make as much sense. Right? Any questions about that? All right, awesome. So I probably should have done these in the opposite order, but it's okay. Part 2, we're looking at the sequence 5, negative 5, 5, negative 5, 5, so on. Right? So think about here, well, the next 2 terms in this are probably pretty obvious. Right, so if we have 5, then minus 5, and then 5 again, and then minus 5 again, and then 5, probably no surprise that the next 2 terms are negative 5 and 5. Right? And the point is each time, and we're multiplying by negative 1. Right? And so if we go on to the next terms, it would continue that pattern. All right. So see if you can write down a recurrence relation for this one. I'll give you a second to think about that. So this one here, what we're just doing each time is we get the next term. Oh, sorry. The order we write this in isn't that important, but probably a good idea to be consistent here. So we'll write the seed value, the starting point, a1 is 5, and then an plus 1 is always just the negative of the previous term, right? Just take whatever we had before, multiply it by -1. And here this n starts at 1. Again, there's no harm in saying, an equals negative an minus 1 and then start your n from 2. Perfectly fine, whichever one you like. Right? Any question there? So the main reason I have this problem here isn't so much to make it a difficult problem to think through carefully, because this one's not too hard to do. It's because I really wanted to talk about how we build in this alternating sign thing. So there's two patterns you can have. If you keep switching from positive to negative to positive to negative, there's two ways that happens. It can start with a positive number like this sequence does, and then go positive, negative, positive, negative. Or it could start with a negative number and go negative, positive, and so on. So there's two ways to get this. Right? So there's two kind of expressions here. The first one, -1 to the n, this is negative on odd indices. Right? So when n equals 1, 3, 5, 7, this kind of expression gives you the negative number. Okay. If you instead want the even indexed terms to be negative, so, A2, A4, A0, things like that, you're going to use really one of two things. You could use -1 to the n plus 1, or -1 to the n minus 1. Either of these would be perfectly fine. Right? These are both going to give you the same thing. Right? So these are negative on even indices. Right? So again, when n is like 0, 2, 4, 6, 8, so on. All right. So with this in mind, we can build the explicit formula pretty easily, because we know it's just going to bounce back and forth between 5 and -5. So the explicit formula, an, is going to be -1 to some power times 5, right? Because it just bounces back and forth. The question is, which power do we want? Do we want the odd indices to be negative or the even indices to be negative? What do we want in this case? I guess I should say here, our first term is A1. A1 should be +5. Yeah, we want it on the even indices, right? Because the first one, A1, is an odd index. 1 is odd. So we don't want this one. And so we can use either of these. You can put n plus 1 or n minus 1. I'll take the positive one. So that'll work for us. And again, if we had started our sequence at n equals 0, then we would use the other one. All right, I thought there was a second one coming. Probably sneak in somewhat right now. Or not. Okay. Hate those sneezes like that. All right, so any questions about this one at all? Great. So let's go into the next problem. The next one's actually really interesting. I quite like this one. It's also a really important concept. So we have 1, 2, 6, 24, 120. So we want to try and write out the next two terms of this sequence. So let me give you a minute or so to think about this one and what the pattern might be here. Take a second to think about that and see what you get. So let me try and remember what the next term is. So to see if you're on the right track here, the next number should be 720. And the term after that should be 5040. I think it's 5040. Did I do that right? Yeah. So if those look like what you have, then you found the pattern right. So what's going on each time here? Right, so here we've multiplied by 2. Here we've multiplied by 3. Here we've multiplied by 4. By 5. This one by 6. And this one 7. Right, we just keep multiplying by the next number. Right, so first by 2, then by 3, then by 4. Right. Does that hopefully look like what you guys were finding? So now that we have that, we can start trying to write down the recurrence relation. So our recurrence relation here, this is one where the recurrence relation will make a lot more sense if we sort of start with the seed value. Start with this. And then say, okay, well, A2, I got that by multiplying A1 by 2. To get A3, I got that by taking A2 and multiplying it by 3. Right? A4, I took A3 and I multiplied that by 4. And so on. Right? So then, for a recurrence relation here, what would it make sense for an plus 1 to be? See if you can pick out the pattern from all of these sort of like individual recurrence equations here. Yep, exactly. Right, so if we look at it, you know, this number here always matches this one and is always one bigger than here. Okay. So that gives us our recurrence relation. Right, so this is one way to do it. Of course, you know, you could write it down the other way as well. So we'd still have a1 is 1, and if we chose to write an here, then this would simply be n times an minus 1. And that recurrence would pick up at 2. So either one would be perfectly acceptable, whichever one you think is sort of nicer here. Right? And there we go. There's a recurrence relation. Any questions about that? All right. So let's try and find an explicit formula then. All right. So again, I'm going to do the same thing I always do here and make a chart. All right. So n equals 1, n equals 2, 3, not n equals n. Do very good. N equals 4 and 5. Right, so we had 1, 2, 6, 24, 120. Right, and let's write down here and see if we can figure out what pattern's going on. Right. So again, I want to, you know, keep this sort of as basic as possible for how we're moving from one term to the next. So here, you know, this first one is just 1. To move from here to here, I multiplied by 2. Right, that's what my pattern up here told me I was doing. Right. Moving from here to here, I multiplied by 3, so this is 1 times 2 times 3. Here to here, I multiplied by 4. That's 1 times 2 times 3 times 4. And going from n equals 4 to n equals 5, that's 1 times 2 times 3 times 4 times 5. Right? So if we look at this here, we can kind of figure out what the pattern's going to be. In each case here, what I'm doing is I'm multiplying all the numbers starting at 1 and going up to whatever the value of n is. Right? So starting at 1 all the way up to 3, for example. Starting at 1 all the way up to 5. So the explicit formula here probably makes sense to say is 1 times 2 times 3 times, you know, n minus 1 times n, right? Just multiply all of the numbers up to n. And this works from 1, 2, 3 onward, right? And so this would be a perfectly acceptable description of that. Is there any question about that? Now this type of expression here, though, this is a pretty special You don't have to write that, but it... Oh, my desktop audio is muted, so no one heard that question. So the question was, do we need that n-1? And the answer is, we don't have to write it. I feel it just kind of helps emphasize that we're taking a step, one number at a time, and we're even multiplying the thing before it. All right. Okay. So does this type of expression here look familiar to you? It may or it may not. You may have seen this before, you might not have. Does it seem like anything you recognize? This is something we call a factorial, where we start at 1 and we multiply up through a number. So like 5 factorial would be 1 times 2 times 3 times 4 times 5, example. Right? And the notation we have for that, and sort of the better way to write this, because, if we had to compute, say, 10 factorial, it would be really exhausting to write out 1 times 2 times 3 all the way through 10. So instead, what we say, our notation for that is n with an exclamation point. Right? The exclamation point here stands for factorial. We'd read that as n factorial. And it just says, multiply all the numbers from 1 through n. So this is the better way to write this down. So I'm going to box that version. Right. This, like I said, this may or may not be something seen in the past, the factorial, but yeah. Any questions about this one? So we'll be using factorials quite a bit coming soon. They'll become very important when we talk about Taylor series. So let's go ahead and there's no questions. Move on to problem 2. All right. Okay. So problem 2, part 1, we're asking, the questions in problem 2 are saying, write out the first 4 terms of the sequence, and then find the limit of the sequence. Right. So what is it converging to, or does the sequence diverge? What's going on? Right. So here we have. Sorry. Here we have this sequence, 10 to the n-1. We just want to figure out, well, what is this doing? So a1, we're just going to plug in n equals 1. So 10 to the 1 minus 1, that's 9. a2, this is 10 squared minus 1. That's 100 minus 1, so that's 99. a3 is 10 cubed minus 1. That's 1,000 minus 1. That's 999. And a4, that's 10 to the 4th minus 1, which is 9,999. All right. So what does it appear that this this sequence is doing? in terms of converging, diverging? Is there a limit? What does it sort of seem is going on here?
The sequence diverge and the limit is gonna go into infinity.
Right. Yeah, exactly. This limit here, right, of this sequence, this limit is going toward infinity. Right? Because each step we take is just going to add another 9. So this number is just going to keep growing. And so we would say here that the sequence diverges. Right? Because that limits, basically that limit is anything other than an actual finite number, so the sequence has to diverge. Right, any questions about that? Awesome. All right, so let's go ahead and look at the next one. Problem 2, or part 2. Let's see, what are we're looking at an equals 1 over 10 to the n. All right. So here we want to write out the first 4 terms and see if this is converging or diverging. All right, so a1, this is 1 over 10 to the 1, which is 1 over 10. A2, this is 1 over 10 squared, which is 1 over 100. A3, 1 over 10 cubed, which is 1 over 1,000. And A4, 1 over 10 to the 4th, which is 1 over 10,000. Right. So you can probably see what's going on from here. If it helps, you can rewrite these as decimals. This is 0.1, this is 0.01, this is 0.001, 0.0001. What does it look like is happening here in terms of convergence, divergence? Does this thing have a limit? Yeah, this limit here is going to 0, right? This fraction gets smaller and smaller each time. So we would say here that the sequence converges to 0. Right? Another way we can think of that, is just sort of working analytically with it, doing limits as we've done them before. The top here of this expression, right? So we're still computing limit n goes to infinity of 1 over 10 to the n, basically. The top is staying 1. The bottom continues to get larger and larger and larger, so this thing has to go to 0. Okay. We could also say here an goes to 0 as n goes to infinity. Right? That would be another way to say basically the same thing. All right. So that's it for this one. Any questions there? Right. And let's look at the next problem. Right. So the next one part 3, we have an is 4n cubed over n cubed plus 1. Right? And again, here we're going to start with n equals 1. All right. So starting with n equals 1 here, let's find the first 4 terms of the sequence. So all we're doing is just, oops, I mean to write n at 1. All right, so you just want to plug in 1. So this is 4 times 1 cubed, so 4 over 1 plus 1. So that's going to be 2. Right? And then a2 is going to be 32 over 8 plus 1. So 32 over 9. Right? A3 is going to be, I don't know what 4 times 27 is. 108. 108 over 27 plus 1. Right, so 108 over 28. A4. So this is essentially 4 to the 4th. 256 on top over 64 plus 1. That's 256 over 65. Right. Now that's not so obvious what's going on. So maybe let's look at these as decimals. Right. This is approximately 3.5556. 108 over 28 is approximately 3.8571. And 256 over 65, that's approximately 3.9385. I'll just use 4 decimals here. So you might be able to tell from here what this is converging to, and I think you just said 4, which is what it's converging to. Question is, how can we be sure of that? Right? Here we have the first 4 numbers in an infinitely long string of numbers. So really, that doesn't conclude anything just yet. We'd really need to look at really large values of n. Or we can use our knowledge of how limits work. The limit, as n goes to infinity, of an, right? This is the limit. Then goes to infinity of 4n cubed over n cubed plus 1. Right? And, you have your choice of how you want to do this limit here. You can use L'Hopital's rule if you're into that. The other thing we can do is say, all right, well, the top is a 3rd degree polynomial. The bottom is a 3rd degree polynomial. We're going to infinity. So the limit is just going to be the coefficient on top and the coefficient on bottom from n cubed. So this limit has to be 4 over 1, which is 4. Right? So when you're doing limits of sequences, just pretend they're the actual function you have there. Right? And so we would say here that the sequence converges to 4. Right. Any questions about that one? That seem to be all right? Awesome. All right. So if there's no questions there, let's go ahead and go on to the next one. Finding limits of recurrence or sequences given to you with a recurrence relation can be a bit trickier because there's no explicit formula to find the limit of. So this one, these types of things, normally you'll either want to get an explicit formula or sort of look at it graphically, right, and make a conjecture here. So, well, we want the first 4 terms of this. So the first term is A0 in this sequence, right? And A0 is 10. Right? I think I forgot to actually add on to this problem, but n should start at 0 here. I think I forgot this in the problem statement. All right. So A equals 1. This is going to be A0 over 10 plus 3. That's 10 over 10 plus 3, which is 4. Right? All right. I think I did that right. Yep. A2 is going to be 4 over 10. Oh, oops, sorry. I meant to write A1 over 10 plus 3, which is 4 over 10 plus 3. Which, we can write this down in a few different ways. You could say this is 34 over 10. Or you could say this is 3.4. A3. So let me take this 30 or 3.4 here. All right, so this is A2 over 10 plus 3. That's going to be 3.4 over 10 plus 3. All right. If I turn this into a nice fraction, right? Really, I want to make this a fraction over 100, and that's actually going to be 334 over 100, right? Decimals, we want to get them out of a fraction, so we'll multiply the top and bottom of this by 10. So this is 34 over 100. This is 300 over 100, so when we add them, we get this. And this gives us 3.34. So what do you think is going to go on here if we continue this pattern? What do you think is going to happen next? Example, maybe what would A4 be? A4 it's going to be 3.334. I think you had maybe one too many zeros or one too many. But you did have A5. A5 is going to be 3.3334. So you might be able to tell now what's going to start happening here. We're going to continue pushing out more and more and more 3s to this. So it's hard to kind of, say it analytically from a recurrence relation. But what's going on here is that, the limit of this thing, an, this is going to push you off to 3, 3, 3, so on, which is exactly 10/3. Yep. And now that I think about it, for some reason, I think I can't do math, and I said 4/3 in the earlier section. But this is totally 10/3. Yeah. So, what's going on here is, we're eventually just going to push this off to just infinitely many 3s in the limit, like that repeating decimal thing. There we go, 10/3. So, all right, so since we're at 120, I'll say there's the Mathematica document for this that shows you how to graph a recurrence relation. I suggest pull that up and look at it and see, see if you can figure out that this sequence is converging to 10/3. It, gets really close to it really quickly. So it shouldn't be too hard to at least kind of visually conjecture that. So, at the moment here, this isn't kind of analytically proven. We've sort of conjectured it. It's a correct conjecture. It is true, but it's not sort of definitively proven. We need to somehow get to a what would we call it? Get to a explicit formula. Sorry, I don't know why that word took so long to come to mind. All right. So if you have any questions, let me know. Otherwise, I'll just end with saying on Friday, we'll talk about how to actually prove, like 0.3333 forever is equal to 1/3. Talk about those kinds of things. That's a geometric series. And I have the videos. I think I just need to put them up, which I'll do now. Well, with that then, have a good afternoon. And I'll see any of you who have office hour appointments. I'll see you later today. Or if anyone wants to stop by during that time, just send an email. Otherwise, good afternoon, and I'll see you on Friday.